Good afternoon, everybody. Really nice to see such a lot of people in person as well as our audience online. My name's Tina Fawcett. I'm the academic convener of the Oxford Energy Network. And before I introduce this week's speaker, I'm just going to give you a quick advert for next week. So next week, our speaker is Isa Damir from the University of Roehampton, and she's going to be speaking about women-led clean energy transitions in rural Kenya. So that's going to be really interesting. It's not going to be in this room. It's, I think, in the desert room, which is upstairs, but there will be signs leading up to it. And the final session is also about energy for development the following week, and that will also be in a room on the first floor. So it's just to look out when you're coming to the next one. We're really pleased to host Doug Parr speaking this evening. Obviously, as we can see, a lot of you are interested to come and hear him, which is great. He's Chief Scientist and Policy Director at Greenpeace UK, and he's currently working on climate change policy in the power, heat and transport sectors. And in the past has worked on lots of other policy areas, including GM crops, chemicals policy, green refrigeration, marine conservation and bioenergy. And his Oxford connection is that he got a DPhil in atmospheric chemistry from the University of Oxford in 1991. So
yes, it was just over there. 2 windows to the right, left of the door. Thank you, Tina. Welcome. Nice to see everybody. Seeing some familiar faces and not too much heckling, please. So the 100% renewable energy. Why would you want to do that? Well, having had a kind of long history in the environmental movement, you're all too aware of the difficulties or challenges with some of the, well, all of the forms of power generation and all the issues with decarbonisation. To some extent, as one former colleague of mine put it, it's choose your poison in terms of how you choose to generate your electricity and in turn electrify the economy. So, but in terms of what Greenpeace has stood for and what I've been looking at, or paying attention to rather, the idea that there are some kind of good renewables, less good renewables, and other stuff that we don't like. And the other stuff that we don't like includes nuclear power for a range of strategic liabilities, political, environmental, security liabilities, the continued use of fossil fuels, even with some measure of containment, because we don't think it's going to be policed effectively and we don't think it's done well. And then there's some other bits of stuff that like mass burned biomass, which strictly speaking counts as renewable, that we're not very keen on either. So it leaves you with a few limited options, which is things like wind, solar, wave, tidal, geothermal. I think that's most of them. And how would you put together an energy system that works like that? Well, that's kind of the challenge. You can say, let's not make the perfect the enemy of the good, etc. But actually, if you don't aim for the stars, then you might not get very far at all. So this is why we're doing it in the first place. A graph that's probably familiar to many of you. This is from the 7th Carbon Budget Report by the Climate Change Committee, so about a year old, but it shows, broadly speaking, we are now 2026, so we're about here, roughly speaking, we're on track. And this is the projection forward, what the Climate Change Committee are hoping we will achieve. But it's all about the UK living up to global expectations and global requirements to take the globe to being net zero emissions by 2050 to try and keep under 1.5 degrees centigrade as a global temperature limit. Now, that was when it was set. Does that look like it's going to be adequate now? Possibly not, because our climate models probably didn't take account of some things like sulfate aerosols and so on, but at least that it remains the goal of British government policy. It remains the recommendation of organisations like the IPCC for how to stay within in 1.5 degree temperature rise. So that's kind of the goal. So how are we doing in terms of delivering on a renewable system? Well, this is just looking at electricity, not all emissions, of course. And we are up around 50% now. So 50% of our energy is nominally clean. As I said at the start, this orange bar, bioenergy, it's a fair old chunk of that. I wouldn't necessarily count that as being properly clean energy. I think there are good reasons for doubting that it is delivering what it's supposed to do on the tin, and it's being heavily subsidised into the bargain. I mean, you could do a whole seminar on bioenergy and what actually, what is sustainable bioenergy and what isn't, but certainly the model we've got at the moment doesn't do the job. There's a DESNZ statistic. So now renewables, the ones that I talked about, wind, wave, solar, tidal, hydro, geothermal, they all, mostly, with the exception of geothermal, they generate electricity. So, as will be familiar to many of you, electrification remains key, but it's only because they generate zero carbon electricity, and then you can spread that electricity through the energy economy into transport, heat, and industry. And that remains the strategy for decarbonisation. Take your clean electricity where you can generate clean power and use that clean power to do the services that it needs to do in the rest of the economy. So the challenge, of course, and always thrown at you by whichever doubter, I put it politely, is suggesting otherwise, is how do you match up when electricity is generated with when it is needed in time and in space? Because as people never cease of pointing out, the wind doesn't always blow, and it goes dark at night. So solar doesn't work. So that's the key challenge. Because you can't store electricity, or at least you can't store it very much. It's not the kind of tradable good that you would see in so many other of the commodities that our modern economy runs on, whether it's metals or particularly fossil fuels. You can't store it, you can't trade it in quite the way that a lot of trading of copper and so on. So you have to. The most effective way of using electricity is to use it at the time that it's generated, close to where it is generated. That isn't always possible. And a lot of the things that I'm going to be talking about are ways of trying to manage the fact that where you generate it and where you need it is not the same at the same time or in the same place. But low-cost storage is meaning that electrification is becoming, I would say, more and more seen as the key to delivering a low-cost energy system, or at least a low-carbon electricity system and a low-cost electricity system. Because things like hydrogen that have been posited as solutions for some of the applications in transport, heat, and so on, just don't look very cost-effective anymore. And they certainly don't look low carbon. They look like a lot of time, energy, and money for not very good effect. Okay. Yeah, I had to talk about that for ages, actually. I'm standing up here talking about that. Anyway, so just as a way of illustrating what I'm talking about, and how important some of these techniques are going to be for allowing electricity to be used in different times and places from where it's generated. This is a diagram that comes from the electricity system operator most recent set of scenarios, the future energy scenarios, published, I think, less than 6 months ago anyway. And here, this is their kind of middle of the road scenario. This is kind of their favored one. and called holistic transition. And looking over here, this is 2050, this is 2025, so it's about now. And you can see our sort of, 50% of renewables is sitting over there. Two things to really notice about that. First, the growth of these green bands, that's wind. Secondly, the growth overall. And that's the electrification of the economy going on. That's the electricity that we generate cleanly being used for heat and transport. And that's why our electricity system, which has actually been contracting in terms of the amount that we need since about 2005, if memory serves me right, is actually expected to start growing again. It's been decreasing about less than 1% a year, but a compound 1% a year for 20 years is quite a lot. But now it is generally expected to start increasing again to something like, well, that's about 750 terawatt hours compared to currently below 300. So it's more than doubling in size, which is why there has to be a very large expansion of electricity generation to meet this need. And even in the middle of the road electricity system operator scenario, most of that is being met by renewables. Now, this isn't, I want to be clear, this is not, of course, a 100% renewable scenario. This is not the Green Deal scenario, but it's illustrative of the fact that the sort of techniques that I'm going to talk about, or the things that we need to do, are actually going to be needed almost whatever happens. It's not just about, a sort of Greenpeace, amazing scenario. Actually, we're going to need a lot of things to handle that mismatch between electricity generation and use under just about any scenario you can imagine, if we're going to keep hitting those decarbonisation scenarios. And I gather Reform were talking some nonsense earlier on today about how they were going to crack Lincolnshire, as far as I can work out, and that was somehow going to solve everything. Oh yeah, and I was paid by Russia to oppose fracking. So that's about those things. Now, slightly complicated one. I just wanted to try and fill out a little bit what I'm talking about, trying to shift electricity around. So this is from that same NESO report. So it's not 100% renewables, but it is illustrative of the kind of thing I'm talking about. There are 100% renewable studies, which I'll mention in a moment, but they don't do as good a diagrams as this. So you can see it from here. So this is 2024. That's what they've called a typical year. This is 2050 and how they think it's going to be different. 2024, you've got the weather-dependent renewables in green. The grey is gas, and the orange-ish colour is imports from mostly France, but other places as well. We have got quite a bit of interconnection kicking off in various places. And you can see there are periods, even now, when we get more generation from renewables, kind of windy spells, storms, quite a lot this last couple of months, coming through and high levels of generation. But there are also periods where variable renewables are generating very little, and that has to be filled by gas. It doesn't always match terribly well the demand, which is the black line going up and down. Some of the gaps are filled in by cheap imports from France. And just occasionally we get these moments where we can either export or we can charge for storage, where our variable renewables are coming to the party. In 2050, NESO are envisaging a different way of working. In the first instance, this dashed line is what they call the, I forget what they call it actually, but it's anyways the demand before introducing demand flexibility, the ability to flex demand from industrial consumers switching off when they're not needed, heating to only operating when it is actually in advance of periods of deficit, consumers responding to price signals. And there are initial experiments with doing that that are showing quite a lot of promise with that. the electricity system operator think there's going to be quite a bit of that. And so these profiles of demand are not following the dashed line, they're following the black line. And the black line matches better, not perfectly, but better, the variable renewables that are available. And sometimes the demand is suppressed, and sometimes and there's when there's a lot of variable renewables, the demand is being increased. The gaps in this case are being filled up in by what they call low carbon dispatchable, which I think is gas with carbon capture and storage, and it's also hydrogen, although it could be hydrogen from renewables or it could be hydrogen from gas, they don't specify. There's some imports and there's some storage as well. So yeah, so these are the things that are going to be become much more dominant in terms of managing the electricity system. There is going to be more variable demand to allow the country to flex those peaks when we have charging of electric vehicles and quite a lot of heat pumps in operation, which could be either for industrial use in things like food processing and so on, where there's actually quite a lot of demand that can be flexed, or indeed at the home. So the opportunity for flex in 2050 is expected to be a lot bigger than the opportunity for flex in 2024. I won't labour this point, but in the summer, you can see conceptually pretty similar things going on, which is that summer characteristically, you've got these peaks in the middle of the day, which is the high representation of solar. Those peaks become very big when there's a lot more solar, as there would be in the 2050 example given here. But you still have some importance of flex. There's still some importance of storage, charging and discharging, and some other bits do play their part as well, demand response and so on. So that shows the kind of system that we're going to be looking at in a high renewables system, which is what we're going to have. Obviously, I want to be 100%, but 75%. A lot of the things we need to do are going to have to be the same, and they're going to have to be made to work. Right. I'll flick over these because it's not very exciting. It's just to say that there are examples of models with the kind of techniques that I was talking about, with an anticipated set of demands from industry, heat, transport, as well as conventional electricity use, where it can be modeled to show that 100% renewables, 100% of those renewables that I talked about can deliver what is required, so that you can make those all mesh up. Unexpectedly, this lot from LUT University in Finland thought that because we've got such a lot of gas infrastructure already existing, it would make sense to turn the electrolytic hydrogen into methane. Interesting, unexpected, but they believe that to be the case. There's University College London with a high-res model yeah, it's very difficult to explain this, so I'll just show the quote, which I hope you can read. So that was another one. There was another one by Energy Systems Catapult did for Good Energy, which is that yeah, low nuclear was basically no more than Hinkley Point, and take away all the biomass, and they could still do a cost competitive model of what the energy system was going to look like. So there are a few models out there. And you could write and say, well, models are models, you can model just about anything. But what I would say is that those, University College London, Catapult, I mean, they're not jokers, right? They are sensible people. And I take heart for the fact that you can do it, and you can make cost competitive models for doing it. That said, my own view is that there are quite a lot of things that need to be sorted out before that can happen. So I would start with some things that are fairly straightforward. Well, they're not straightforward, but they are conceptually straightforward. Most obviously, you need to have a lot of renewables if you're going to do that. So lots more rollout of offshore wind. You've got to do much more on the grid. And that includes storage, it includes smartening it up, it means smart meters on businesses as well as domestic. Take advantage of all those opportunities for system cost savings through demand response, where the system cost savings can be shared with the consumers in question. You need to electrify vehicle transport, obviously. Say more about that in a moment. And we need to roll out the heat pump program. And as I say, conceptually straightforward, probably practically rather more challenging. How are we doing on each of them? Well, so you might remember from that diagram I showed from the NESO that big, thick, dark green band, offshore wind has to do a lot of the heavy lifting. And the target for 2030 is about 45 gigawatts ish. I think for 2050, we're probably looking at 100, north of 100. Royal Society said 100 to 140 gigawatts. So that remains quite challenging. Even so, over the 20 years after 2030, we still need to build another at least 50, 60, rolling out at 3 to 4 gigawatts a year. Onshore wind and solar are still growing a little bit too slowly. I mean, solar is accelerating because it can now go merchant. Most people can stick it on the roof and find it is profitable. Certainly, buildings with good use profiles, in other words, they match the solar quite well, will certainly do so at a profit. The local power plan was launched not long ago, which is a way of rolling out renewables to local authorities and communities. I'll mention it a little bit more later, but I can't see any. I just can't understand why we don't just say every school, hospital, and public authority building should have solar. Anyway, I digress. But onshore wind is probably growing still too slowly. Costs of offshore wind and onshore wind have gone up lately. Onshore wind, actually, in real terms, has probably been about flat since 2021, judging by the auction prices. But appetite for supporting renewables has diminished, unfortunately. The storage pipeline is growing quite rapidly. Storage is growing quite rapidly. It's now 7 gigawatts, and the pipeline. Well, I'd like to tell you what the pipeline is, but I seem to have missed out the number. I think it's about 45. See, I looked it up and then forgot to put it in. It's something like
42, that. So you said 42 at 2030 is not the point.
Oh, right. 2 gigawatts per hour. So, yeah, so there is 42 gigawatts per hour for 2030. The pipeline is actually much larger. It's about, I'm feeling it's about 70. But the 42 gigawatts is the one that's got the preferential grid connections for 2030, and there's another set that have got grid connections nominally for 2035, which I think is up towards 70 in total. Sorry, I forgot to Failed to put that number in. Anyway, that's how, roughly speaking, how we're doing on those. So there's still work to do there. On the grid, it is changing, but for far too long, the offshore wind approach to grid has been out of date because it's had a point-to-point connection instead of a system-wide grid. And now we're a little bit playing catch-up, trying to create something that looks more like an offshore grid as well as having an onshore grid. There is an awful lot to do in terms of creating an offshore grid. This is from the 2035 assessment of what's called the holistic network design, which is to include those offshore connections. There's an awful lot going from Scotland to the south of England, and that's going to cost quite a bit. We need to put wind farms where they do least damage to wildlife and plan the offshore grid accordingly, I would say. There's a pragmatic political reason for that, and there's a kind of normative reason for that, which is you don't want to be saving the planet by killing off wildlife. That doesn't really stack up. And wind farms that are damaging to wildlife and cables that are damaging to wildlife will get held up by legal challenges. I can assure you, I know the environmental community and they will do that. So avoid it, plan carefully. Spatial planning. Yes, there's a lot to build. Right. Heat pumps. European Heat Pump Association produced a list of sales of heat pumps. For those who can't see at the back, you can probably guess where we are on this diagram. Yeah, there we are. We're right down. We used to be next to last, but I think Hungary is no longer part of the European Heat Pump Association, so it's dropped off the list, and now we're gloriously taking up the wooden spoon. So it's true that heat pump sales have gone up. They are going up year on year. They're probably not going up as fast as they need to go up, or in fact, they're not going as fast as they need to go. They need to go up a lot quicker. So the government target has been shifted to, I think, 450,000 installations a year by 2030. But in a sleight of hand, they changed that from not including new build houses to including new build houses. And a lot of new build houses will have heat pumps installed as well, it will be required if the future home standard is actually published, as it's been promised for about a year now. Or maybe we're getting quite close. So they're going to come out in Q1, I'm told. So we've only got 5 weeks left to wait. So UK needs a much expanded heat pump program. Various ways to do that. I'm not going to talk about those now. Key challenges. So those were kind of 4 examples of things where we kind of know what to do conceptually. It's just a matter of getting the technology in place, finding ways to finance it, finding ways to make it happen, doing the right kind of coordination. Here are some of the things where I think a real 100% renewables system is going to find itself a bit challenged with technology as it stands at the moment. Going back to the theme of this talk, I would say, even if you're talking about 75% renewables system, you'd still have a bit of a challenge with some of these. Maybe you could exempt 1 or 2 sectors, but a lot of these things would have to happen anyway, one way or another. In particular, long duration storage, I think, is going to be a requirement under just about all systems. Working out what to do with heavy goods vehicles, I think we're moving in the right direction on that. Industrial heat remains a challenge, green steel too, ditto aviation. So let me say a little bit more about where we are on each of those, and where I see the opportunities for some some movement really. So long duration storage. Here's 3 examples. It's quite hard to tell what they are, isn't it? But top right, we have, this is where I really could do with my notes, but top right is a hydrogen and salt cavern, which is, as I understand it, 95% constructed and is due to go into operation this year. It is, I think, 200 megawatts of electrolytic hydrogen production from renewables in Utah. It's great having to do talks like this because you find out stuff that you didn't know about before. And I was completely unaware of this until I was poking about, trying to say, well, okay, where's our biggest green hydrogen project in the world? And well, that's not actually it, because it doesn't look like that. But that is a mock-up of these are salt caverns down here, and it's the hydrogen plant there, and it is 220 megawatt hours. Sorry. But it is at the end of 2025 to 95% complete. So green hydrogen is one of those things that really could be long duration storage. Well, we know how to store hydrogen. We've been using it for years, decades. So once we've got it, we can store it, and we know how to burn it. In fact, usually the challenge is to stop burning it, not burn it. So we're all good with that. Now, liquid air, it's one of my favourites. That's the one in the middle on the left. Again, I found out the biggest plant in the world for liquid air storage. You cool down air until it's a liquid at -195 centigrade, and then when you want your electricity back, then you allow it to warm up and blast the air through a turbine. When I was in the lab over there, I used to be really worried about liquid air, but apparently it's all right, it's all fine now. It doesn't blow up, which is what I was told it would do. Anyway, the biggest plant in the world is this one, which is in the Qinghai province of China. But it is going to be supplanted, in theory, by a project that is underway already in a less exotic place, which is Manchester. And that's a company called Highview Power, which is a UK company, and they are investing in it. They've already got a pilot plant in California. So they are going to have the world's biggest plant, which is storing liquid air. Again, not huge, 50 megawatts, and I think 6 hours of storage, so about 300 megawatt hours. But still progress. And on bottom right there, that is a plant which is a high density hydrogen plant, which is being commissioned. It's just being commissioned actually in Plymouth, where instead of using conventional hydro, I'm sure people are familiar with. It's very simple. You have water at the top of the hill, you let it run down the hill, and it hits your turbine, and you spin it. And then when you want to store, you use a pump to pump it back up the hill again. What these guys, Re-Energize, are doing is saying, well, trouble is you need big high mountains for that. Not everywhere's got big high mountains, but a lot of places have hills. So if we have a fluid that is 2.5 times more dense than water, then we don't need anything like the height of the big Scottish mountain, and we can have it, well, in Plymouth. So they have commissioned the plant. Obviously, with all these things, how big can you scale? At what cost? How easy is it to actually make it work? Are you going to hit some snags along the way? All of these things could happen. But it shows that there's actually, I didn't include flow batteries in that. there are lots of ideas around, and some of which are edging towards mainstream use. So the green hydrogen, I mean, just to, you know, I was looking into it because I knew green hydrogen, storing it in salt. What have I done there? That was clever of me, wasn't it? Why did I do that? Like, yeah, there we go. If you, you know, there was a very large program of green hydrogen projects around the world a couple of years ago. It's diminished somewhat because partly because the costs are more challenging than expected, shall we say, and particularly as it comes alongside waning government support. But they're still going. They're still being trialled. There are others in China. I'll mention those in a minute or two. You know, I think liquid air, green hydrogen is something where you can store the gas for interseasonal. You can store it from summer to winter or winter to summer, depending on what the weather's like. And over several years, if you want strategic reserve. Your liquid air, well, liquid air will warm up, whatever you do, you know, so we're storing it for at most weeks. And this stuff is going to be more like conventional hydro or pumped hydro, I think, where you're expecting to reuse the fluid over days rather than, and possibly even hours, rather than months or years. I think the thing is that battery storage is becoming so cheap that the use of hydro as pumped storage is sort of daily churn is going to look less appropriate because batteries are going to eat their lunch in terms of what they do. At least that's how I see it. So anyway, the point of this is to say, look, long duration storage, massive challenge. Things are happening, and slowly things are getting underway in various places. Heavy goods vehicles, well, used to be thought of as the big challenge. Don't quite know what to do. How can we challenge these things? It's not possible to move things around. Well, actually, the rise in energy density and the lowering of cost of batteries has actually started to solve this, and you start to see companies like Amazon make really quite large investments in fully electric 40-ton HGVs. You know, Amazon are not known for being kind of, you know, profligate with their cash. They are going to be quite switched on to that. They've done a trial. They knew they could make this work. So this one, I think, is on the way to being fairly clear. There were competing ideas about hydrogen, and then those things where I can't remember what they're called now, but they run along motorways and you can attach the HGV to them. Probably won't be needed. Green steel, here's another one. So, Pete, I need your notes. Okay. I need your laptop so I can remember my notes. Steel, about 8% of emissions globally. So, normally smelting is done with coal, and it's not as simple as just using energy, because it is the reduction of the iron ore to iron requires that you have a reducing agent in there, and so the coal is acting as the reducing agent, not just as the fuel. So if you put something else in there, it's got to do both those jobs of providing heat and providing a reducing capability. There is a way of doing it with hydrogen, and there have been a number of projects around. Actually, there's a lot of projects around. Not many of them are operating, and that's kind of the challenge. The one that I could see that was operating, which is only using 70% hydrogen, was, again, it's one of these things. If you start doing a presentation like this, you find this stuff out, right? So it is in northern China, 600,000 tons a year. That's that one there. That's making about a steel plant about as pretty as it could be. I mean, I have pictures of these things. I mean, maybe if you're a chemical engineer, you know what it is. I mean, as far as I can be concerned, any of these could be an acetone plant in Runcorn. I mean, couldn't make Runcorn look that pretty though. So yeah, that's the biggest one that I'm aware of that's actually operating. Again, you know, quite small. 600,000 tons sounds like a lot, but Chinese steel production is 1 billion tons a year, so it's not enough, about half of 1%. So there is also German project in Duisburg that is going to be operating in 2026, I think. This is the ThyssenKrupp one. Sorry, 2027 is that one. And then there is far right there. There is the one that has had a bit of economic troubles recently, but is still going. It's used to be called HT Green Steel. It's now called Stegra. Yes, and that's in northern Sweden, taking advantage of the hydro to produce the green hydrogen that can be then used in the green smelting plant. So I think this one, I think it may be another one in Germany that's got just another 300 million euros from the German government. So it's still kind of inching its way forward. So the Europeans haven't completely given up on it. There are a few projects going on in China. So, you know, it's still happening and it's still possible that our 100% renewables projects can contribute to creating green steel. Once you've got it out of there, you can put it in an electric arc furnace and doesn't feel like it. Industrial heat. Well, this one is also a bit challenging. Some stuff seems very clever, and some stuff seems pretty straightforward, because this is just the way you get high temperature industrial heat going up to 1500 degrees is you run electric wires through bricks, and that's it. And you can heat these things or sand up to 1500 degrees, and then when you want the heat, you can you just blow air through it. Now, I make it sound very simple. Actually, getting the engineering right, I think it's a lot more complicated than that. But this is a 100 megawatt plant in Portugal, which is due to go online next year for beer making. Yeah, beer making. And it's in Portugal because they do have quite a lot of variable renewables, so they can use that to heat up. It doesn't matter, you know, you've got well insulated brick. You can hold the heat there for months if necessary. So you get the variable renewables, and when you've got plenty, put it through the bricks, and then you've got the heat available when you want it. Why you need 1500 degrees centigrade heat for brewing beer is beyond me. Right? Maybe there's something about Heineken. I don't know. Anyway, that is what they're doing. So, aviation. Yeah, this is one of the really challenging ones, because there's quite a lot of ideas about what you could do. But let's be honest, I don't find any of them very convincing. Maybe they'll all chip in a bit. Electric planes. I think the energy density of batteries is still nowhere near what it needs to be for long distance flight. But I think there was one study not long ago that said about, you know, could maybe get about 15% of emissions could be tackled by electric planes if kind of battery chemistry keeps on the trajectory that it is. Hydrogen planes, I know there are still companies who are trying to make that work. I don't think it's going anywhere. Sustainable aviation fuel. This is what Rachel Reeves talks about when she says that Heathrow is going to be fine and won't increase emissions. It's not true. Sustainable aviation fuel seems to have inside it a lot of the same assumptions that were fully and comprehensively rebutted around the biofuels debates in the noughties and in the 2020s. So, you know, we've had a load of smart people coming thinking that they're going to solve this problem with exactly the same stuff that's been known to fail before. So, I mean, there is some sustainable aviation fuel you can get from genuine wastes, but it's not a lot. I mean, it's middle to low single digits, I would say. And, you know, there's no problem with doing it. I don't have a problem with that. But, yeah, let's not imagine that you're solving the international flights issue by doing that. E-fuels, well, these are fuels that you create from the fusion of hydrogen and CO2 to make methanol and then do some other chemistries to create kerosene. Maybe, but maybe not, because they're going to be quite expensive. I don't think there's any way around the fact they're going to be expensive, because you've got to put a lot of electricity in to get the hydrogen, you've got to put a lot more energy in to make that into methanol, and then you've got to do more synthesis to create fuel. So, yeah, very, very cheap electricity is going to be required before that's going to be considered a go by the aviation industry. Now, you could say, well, you know, making fuel expensive is a really good idea, actually. You discuss. And then the other thing that the Climate Change Committee flagged up in their last set of advice actually was, well, you know, maybe the aviation industry should just pay for removals. They should just pay for capturing carbon dioxide from the air and shoving it underground. Maybe that would be the way. But again, same as e-fuels, it's going to be really expensive. That said, if I look where we are temperature-wise, I mean, we're going to have to get used to removals somehow. So maybe the aviation industry would be the right way to do it. So I don't think any of those is any kind of comprehensive plan. They might sort of each chip in a few bits. Now I am of course at the point where I would where in my preparation for this I started to run out of time. So I'm just going to race through a few final slides about where I was brainstorming with myself what needs to change. I'm sure you'll have your own list. This is a thing that I keep coming back to, and I've conspired in this today by imagining that this whole thing is some kind of technological process, and it is a technological process, don't get me wrong. But if you look at the changes that we're talking about to transport, heat, electricity, industry, it's not just a technological process, it is a political, economic and social project as well. And by pretending it's not, I think we do a disservice to the entire proposition. Because yes, 100% renewables for sure. I think we can say it's plausible. There's enough around to say it's deliverable. But, you know, I don't know what the cost would be. That's still to be explored. And above all, again, irrespective of whether it's 100% renewables or 80% renewables, there are some big changes going to come on there. And we've got to be really mindful of those as we go through it. So first and foremost, some communities are going to be hit hard, and they will need support. A lot of this focuses on the northeast of Scotland around Aberdeen, but you can see the same dynamic playing out in Port Talbot, Scunthorpe, where the old-fashioned blast furnaces are coming to an end. That decarbonisation is not the reason they're closing down. Those plants have been losing money for ages. But if they're going to be renewed, then this actually could provide an opportunity rather than a sort of hazard for those places. But there will be communities that will be hit hard. Community energy is a total winner, right? You involve people, you engage people in community energy. They start to participate in the transition. It becomes really important that they can see what is going on across the piece in terms of how their little project, and it probably will be a little project because community energy is quite small generally, how that fits into the wider scheme of things. I could say more about that. Right. Interestingly, polling evidence, clean energy is a very attractive frame. If you talk about, you know, tackling climate change and the cost of climate change, you get polarization in most countries, actually, to some extent. But it's started to become quite a thing in the UK, where climate action is seen as a polarizing issue between particularly left and right, unfortunately. If you talk about clean energy, it is not polarizing. It polls at 55% approval with reform voters. Clean energy is different from the mindset of, climate action, doing things to cut net zero. And just throw away line. Just sort that out, will you, somebody? But it's becoming a massive problem. I mean, not just in the climate space and in the energy space, where all sorts of snake oil salesmen are parading their wares on TikTok. But across a whole range of policy issues and institutional kind of arrangements, really. Okay, a few more things of what needs to change. I realise I'm running over time, so I will rattle through these. Internationally, I think, and we start to see this emerge because the climate talks are generally not achieving very much. It's a long time since the Paris Agreement struck a deal that we would all collectively get to stay below 1.5 degrees centigrade. It wasn't operationalised, but at least it was an agreement. Even the semblance of agreement has now fallen out of the climate talks, whereas there are coalitions who will get together to operate in favour of particular technologies, and we can see how potentially those groupings could work for technologies that shift around that can be used in different geographies. So again, a bit of a throwaway line. How do you get, if we're not going to renationalise the entire electricity system, how would you get to integrate all these technologies together? At the moment, I don't think we've got that anywhere near right, because the things like the capacity market can be gamed, etc. I think we do need more explicit innovation policy for some of these areas that are more challenging. And I don't mean like science and science budgets. I mean deployment budgets, early deployment budgets, because that's where the real learning goes on. Don't stick all those innovation and social costs on energy bills, because you just damage the whole thing. Right. So, in summary, 100% renewables is plausible. Yes. Okay. As I've been saying, many of the most outstanding challenges apply to decarbonisation generally. But there are nascent scalable technologies that we can use, and that's it. I thought there was a thought, but that's it. Thank you very much.